Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 8. Multistep Methods, Adams-Bashforth and Adams-Moulton Methods. One-step methods require only prior value yi to compute current value yi plus 1. That is why they are referred to also as self-starting methods, because the marching process can start with the initial value. In the following steps, several prior solutions, yi minus 1, yi minus 2 and their derivatives y prime I minus 1, y prime, I minus 2, and so on become available. We can use this information to extrapolate the current estimate, which provides important details about the curvature of the true solution. Methods making use of more than one prior step estimates are referred to as multi-step methods. The main idea is to make use of y and y prime from prior steps to construct a high-degree interpolating polynomial for estimating the current step, yi plus 1. A linear n-step scheme is generalized as where fi equals fxiyi denotes the first derivative at xiyi, and alpha k and beta k are the coefficients of the interpolating polynomial. For beta 0 is equal to 0, it corresponds to the explicit Euler method. The implicit formulas are more accurate and stable than the explicit ones. However, they require a root-finding algorithm to obtain the current step value. Recall that the one-step methods used a linear extrapolation with an estimated slope to calculate the current step value. Multi-step explicit methods use polynomial extrapolation by using polynomial fits from previous step values as illustrated. Consider the first-order model initial value problem with n known prior estimates, computed by a one-step method of the same order or better. Integrating the initial value problem over an arbitrary interval leads to the integrand is approximated by an n-1 degree polynomial passing through n uniformly spaced points. A Lagrange interpolating polynomial for the integrand is constructed as follows, where Lkx denotes the Lagrange polynomials, defined as, and Enx denotes the interpolation error. Substituting the interpolating polynomial into the integral expression and integrating yields so-called Adams-Bashforth formulas. Generally, uniformly spaced steps are preferred due to the ease with which the interpolating polynomials can be constructed, resulting in minimum CPU time. Adams-Bashforth formulas are expressed as, where fk is fxkyk, and beta k's are the Adams-Bashforth coefficients. In second-order Adams-Bashforth, as illustrated, two prior estimates are required. In third and fourth-order Adams-Bashforth, respectively, 3 and 4 prior estimates are required. The coefficients of the Adams-Bashforth method for orders 1 through 6 are presented along with the local truncation errors. The Adams-Bashforth formulas for the second order, third order, and fourth order are explicitly presented as shown. The advantages of the Adams-Bashforth methods are: Adams-Bashforths require only one derivative evaluation per step, as opposed to 4 evaluations per step in Runge-Kutta methods, making Adams-Bashforth schemes considerably faster. Adams-Bashforth N gives the true solution for the initial value problems, whose true solution is at most an n+1 degree polynomial. The disadvantages of the Adams-Bashforth methods are: the Adams-Bashforths require multiple prior step estimates in addition to the initial value to advance forward. Starting values are obtained with a one-step scheme, which should have the same or higher order of error as the Adams-Bashforth scheme used. With an increasing order of Adams-Bashforth, accuracy increases while the stability region shrinks. Adams-Bashforth formulas for non-uniformly spaced cases are complicated and CPU time-consuming. The Adams-Moulton formulas are derived in the same manner as the Adams-Bashforth, with the current step estimate E+1 is also used in constructing the interpolating polynomial in addition to the prior step estimates generated from uniformly spaced points. A Lagrange interpolating polynomial for the integrand is constructed as follows, where Lkx denotes the Lagrange polynomials, defined as follows. Substituting the interpolating polynomial into the integral expression and integrating yields so-called Adams-Moulton formulas. The Adams-Moulton formulas with uniformly spaced steps are preferred due to the simplicity and ease of constructing interpolating polynomials, efficiency, and less demanding on CPU time. Adams-Moulton formulas, AMN, are expressed as follows, where Fk denotes Fxkyk, and beta k's are the Adams-Moulton coefficients. The coefficients of Adams-Moulton method for orders 1 through 6 are presented along with the local truncation errors. For n equals 1, the AM1 corresponds to the implicit Euler scheme. The Adams-Moulton formulas for the second order, third order, and fourth order are explicitly presented as shown. The advantages of the Adams-Moulton method are: AMs are implicit schemes. High-order AM formulas are available. Adams-Moulton schemes are more accurate than Adams-Bashforth schemes of the same order due to smaller truncation error constants. Adams-Moultons have larger stability regions than Adams-Bashforths of the same order. To minimize the CPU time, function evaluations can be reduced to a single function evaluation per step by shifting, copying, the estimates from prior solutions. The disadvantages of the Adams-Moulton method are: Adams-Moultons require a high-order single-step scheme, such as RK4, to generate a sufficient number of starting values to start Adams-Moulton marching. Adams-Moultons require larger memory allocation due to the need to save the required number of prior estimates. CPU time increases due to iterative algorithms applied in cases where the use of a root-finding algorithm is required to find the root, current step estimate, of the nonlinear equation. The convergence of the root-finding methods depends on the differential equation, i.e., fxy. Let us consider the following first-order initial value problem. We wish to use the second-order Adams-Bashforth and Adams-Moulton methods to solve the given initial value problem up to x equals 1, and obtain solutions for h equals 0.1, which we will compare the estimates with the given true solution. We begin with the given first-order initial value problem. Isolating y prime gives the slope function fxy as minus y over x plus 1. The initial values x0 and y0 are 0 and 2, respectively. For h equals 0.1, the abscisses run from I equals 0 to 10. The difference equation for the second-order Adams-Bashforth method is obtained as follows. Note that to start the marching, we need to know two prior step values. Thus, the subscript I must start from 1, and y1 should be obtained with a one-step method of the same or higher order of error as the Adams-Bashforth method. Here, we will use the exact solution. Substituting f into the difference equation, we get. The final form is a recursive equation requiring two prior values. For I equals 1, the equation for y2 becomes. Substituting the numerical values, we obtain 1.67248. For I equals 2, using y2 and y1, we find y3 as 1.544,112. We continue the recursive procedure in the same manner for y4, y5, and so on until x equals 1 is reached. The computed estimates are presented in the following table. The first two rows are required to start the marching. The first one is the initial value. The second one was generated using the true solution. But, in practice, we should also estimate this value using a one-step method. Recall that the local truncation error for this scheme was 5h cubed over 12. The global error is second order. Notice that the arithmetic average of the true absolute errors is 0.742 times 0.1 squared. The second-order Adams-Moulton scheme takes the following form. Since this method is an implicit one, fi plus 1 contains the current step value, yi plus 1, as well. When the f function is nonlinear, the resulting difference equation gives a nonlinear equation for the current step, and a root-finding algorithm is required to obtain yi plus 1. However, since f is a linear function, we can easily isolate the current step value as follows. Then, the marching process is no different than the explicit methods. For I equals 0, we obtain. Substituting the numerical values, we find y1 as 1.8173,913. For I equals 1, using y1, we obtain y2 as 1.6653,913. We continue the recursive procedure in the same manner for y3, y4, and so on until x equals 1 is reached. The computed estimates are presented in the following table. The arithmetic average of the true absolute errors is 0.165 times 0.1 squared. The average error is about 1/5 of that of the AB2 method, which should not be surprising since the local truncation error of AM2 is exactly 1/5 that of the AB2. With this note, we end this video lecture. That is all for now. See you next time with another topic. Bye.